Yeah, attendance has been downloaded. Okay. Okay, so what did we discuss in the last class? We saw some of your submissions as well, like for the high rise, and yeah, before that we talked about foundation designs and stuff. Okay, now now I want to talk about more on structural failures and reasons for structural collapses, and how things could be averted, like saved from failing, and what happened in some of the structural failures also. So we'll move towards that, and we will also see what are the what do you call, there are some evaluating techniques of a structure, right? Before we want to retrofit or rehabilitate a structure, like there is a building, you want to redevelop it, or it's repaired and it needs to be retrofitted. Before we do that, we need to assess what's the strength of the existing structure, right? Now, how much we can make use of it before we build on top of it or modify it and things like that. So, and also you can assess the structure for its stability and safety in its present condition. That happens because, see, a structure could be like 20, 30 years old, right? Any sort of building. It could be for example, take a commercial complex or a public building. So within that 20, 30 years, your building codes, which supervise the entire design, construction, and serviceability of a building, it could change. For something would have happened, there would have been a seismic event, which lessons would have been learned, and they would like to incorporate something in the code. So when such a code comes up, the existing buildings need to be checked if they can perform for the new clauses in the code, in the new code, right? So in order to do that, you need to evaluate the building, right? So it would have been built for certain, for example, column sizes could have been something, and it could have been designed for a certain amount of force earlier. Now you have a new revision in the code, which says, no, you need to step up, you need to analyze for these extra things, and your forces for design would have been increased, right, analytically. And what do? You go back to the structure and you need to check for the increased forces. Are they going to survive? Like, are they have been sized, and is it like, is it okay for the increased forces? Like the same existing sizes could prevail or not. So for those things, you need to evaluate the structure, right? So in order to evaluate, what happens is, okay, you already know the structural size, and you know the concrete grade that has gone into the structure, like theoretically, because for example, M30 is the grade with which you are used, and you know it's M30 is there, and you do your new analysis according to the new codal provisions and find out you require, either you need to step up the what do you call, column size. For example, if it was already 500 by 300, now you need to step up to 450 by 550, something like that. Or you can increase, or your column grade, the strength of the column could have been more. Like if it's M35 instead of M30, it would pass, right? Because your capacity of the column depends on its size, its material strength, and the reinforcements that it's gone into it. Now, okay, you don't want to increase the column size, right? Now, what do? You need to analyze or assess, or a better word is determine, what is the actual strength of the concrete that has gone into it. Because if it's M30, in most of the cases, it won't be actually M30, because we always build something, pour the concrete for a little bit higher strength. It could be, it could be speculated to be around like something more than M30, like it could be M35, 40 or 45. Okay, in reality. Because that's how the mix designing will be done. You want M30? No, we are not going to pour exactly for M30, right? In your mix design, your constituents, like your cement, sand, aggregates, and water content, excuse me, are designed, and they have a target mean strength which is higher than your required grade. So target mean strength is something higher. So once you want to achieve that, there are so many things that can not go perfectly as intended and as designed, right? So we always step up. We always conservatively go for something around M38, M40 or something. And when you actually test the concrete, it would be something higher. And concrete always keeps on increasing its strength. Not so high, not so relatively high as it increases in its initial 28 days, right? So it gains strength tremendously faster in the initial 7 days, 10 days, and you test the concrete at 28 days using a concrete cubes and things like that, right? And you determine, yes, the structure which has been built with this particular concrete is confirmed to have this particular grade, minimum grade. So you test the cube at 28 days, a sample cube, which during your pouring you would have collected samples and you test it on 20th day, this particular sample. And you are getting 35, 36 MPa, okay? And you say, yeah, fine. So whatever the concrete that has gone into is most likely to be having M30, minimum requirement is that. Okay, fine. So after 28 days, the strength of the concrete also keeps on increasing, but not at a very, not at that level at which it was increasing earlier. So you reach, some other grade, eventually, because the building would have been there for 20, 30 years old, but you cannot think like it's gonna now be like magically M50 or something. No. So it could be slightly higher. It could be like, 2 MPa or 3 MPa higher in its period of lifetime, right? So as I told, in your assessment, you need to increase your size or your concrete column grade would have, if it is higher, then it would pass. Because theoretically it was M30 when it was designed before. Now you need M35, you go do a testing. Like what you do, there's something called partial destructive testing. You take samples like core, like a cylindrical core, which is cut from that particular column, okay, in a location. There are some dimensions for that. And you cut that concrete, actually, you take a piece of the original structure and you, in the laboratory, you crush it and, test it up to failure. And you know what load it fails, and you reverse calculate and you find out, okay, it is of now, the strength is 38 MPa or 40 MPa could be. So you do that. There are some, this is a partial destructive testing. What I mean by destructive testing is you break it, right? That's destruction. So, but you cannot actually break a structure because then it doesn't serve the purpose of a building. So you take a sample out of it. So that's what you call as partial destructive testing, and you test it, and you need to fill that hole up, in order to retain it. So that is one. There's something called non-destructive testing, NDTs, non-destructive testings. You pass a ultrasonic wave inside the structure, and it goes and reflects back, and then it comes back to your transducer. And with the velocity at which it goes and comes back, there are some equations which tells you what is the quality of the concrete that is inside. It's good if it is faster, the wave can travel faster in solid. So things like that. Or there's something called Rebound Hammer. Like you have a small instrument which is having a spring mechanism and a hammer at the end. And it's like a small gun. You take it to the surface of the concrete and you take some measurements out of it. You press it, so it goes. Hits the concrete and comes back, and depending on its spring constant and how much it can deform, and your instrument gives you a reading. Okay, and there are some formulas. Again, you estimate the concrete strength based out of that. So these are the methods. So and when you do that for the entire building, okay, you're building here, all these structural strength is like it's fine. It's more than the requirement. It could pass, right? You don't have to retrofit the structure, or if you have to, then what you have to do, then you need to increase the size of the column, right? There's something called column jacketing, where they pour an additional thickness of column around the existing column, or you can use CFRP members, like carbon fiber reinforced polymer, like a fabric which is having very high strength, and you wrap it around your column, and there are some chemicals you apply on top of it. Once it sets, it's very strong. It's stronger than steel. It's basically 3 to 4 times stronger than steel. But its thickness is very, very small, like in terms of like 3 mm, 4 mm, 5 mm. That's the only additional material that you wrap around your column and you retrofit it. Obviously, it looks not so pleasing, right, to the eyes, because it's the carbon fiber material. It's a black colored material, so your column would be totally of a different color, and you need to cover it with some some cladding material that would occupy some space. So it's always give and take between what you want structurally, functionally, and what you want architecturally. So instead of having a CFRP and you want to cover it with another cladding material that would occupy some space, and your net effective floor area gets reduced, right? Your rental value depends on that, because you get rent from your tenant based on the square feet in terms of commercial buildings, right? So once your square feet reduces because of so many number of columns being increased, that's something to consider. So either of these two you can go, or you can go for column jacketing. It's like you increase 50 mm or 100 mm of the concrete, all around, and do it. So that is something called seismic, sorry, not seismic, it could be for any forces, right? So you evaluate the structure and see if it's safe. So that's a kind of structural evaluation or assessment. And if you want to retrofit or repair it for these conditions, or something like you want to increase 2 more stories on top, right? For that, you need to assess if your entire structure, including the foundation and the soil below, can and is capable of taking 2 more stories that you want to build on top of the structure, right? So things like that. So we'll see some of those retrofitting, repairing and assessment methods and mechanisms, right? That we'll be seeing later, along with after we look at a couple of structural collapses or structural failures, because with structural failures, we understand a lot about how do we want to design the structure, because we design it to avoid the failure, right? We want to know what's the extreme if the structure is loaded in a particular case, at what point it will break and how it will break, like what is the sequence of breaking. What collapses first, the slab, the beam, then the column, right? Or is that your required way of collapsing? Or there could be something like the other way, like you need to know what collapses first, and you need to design in a way like you want to minimize what do you call a global collapse. If something is going to collapse at the end, okay, at the extreme end, when the load is like it's reaching its ultimate, we want to tell which part needs to collapse, right? So that in a way the entire structure doesn't collapse. So we prefer local failure over a global failure. Okay, things like so. Once we look at structural failures, what has happened, we would be in a better position to design it so that it doesn't happen in a catastrophic way, and we can learn a lot from it actually. So that's what basically in structural engineering, when you go to laboratory testing, we test the material to failure. Not only the material, a structural component. We test the component like concrete beam or a steel beam, an entire concrete slab, columns and walls, in whatever possible ways, in downward loading or like lateral loading. Some of the laboratories have those facilities to test particular structures for its extreme. Okay, and from that we learn, okay, it's failing in this way, it's failing in the way that we had intended, and it's failing at that particular load or something more than that we designed it for, right? So that we know, okay, this load is not going to happen in the building. First point. Second thing is, if it happens also, we want it to fail in the way that we want it. Okay, not in some other global failure way or not in some catastrophic way. Right. Having said that, let me share my screen so that we can go into today's presentation. Just a second. I'm already sharing my screen. Sorry. Okay, so I want to cover quickly about something on composite structures. What are the things to consider in design, and how it is constructed? What are the things, construction challenges we have? What are its advantages, and what could be its disadvantages if you could think about it and come up with some. And we'll see a design example of the difference between designing something using a traditional concrete, like traditional reinforced concrete structures, RCC, or something with composite structures, right? Okay, this presentation I had done previously, for some other purpose, so it has this overview of the presentation, which we don't have to see right now. We'll go straight away, right? Okay. Now, what is a composite? A definition of a composite is basically it's not a single element that is in a composite. The term composite is like you have more than one element. It could be 2 or 3 elements, like which are individual. Why they are not the same? They have different properties. So 2 distinct materials that come together to serve a common function, right? So concrete and steel are basically composites by nature themselves. So that's why we call them as, for this definition's sake, traditional composites. Okay. Now composites, there are two things: traditional and advanced composites. We'll see what are advanced composites. Now steel concrete, most of structures, how it is designed and built in the past decades, it's a traditional composite. It has steel. Steel is good in tension, as we have learned. It is also good in compression, right? But the cost is higher. We don't want to generally build everything with steel. Its cost is relatively higher when compared to concrete. Now, what is concrete made up of? Concrete is made up of earthly materials and, of course, cement. Do you know, like, concrete is the most used liquid after water in this entire world? Like, it is used so much because it can be cheaply made, and it can, like, occupy any form. And once it gets solidified, it's good to go. So concrete is a very like a magic material. And that's why it's most commonly used. Now, concrete in conjunction with reinforcement steel. Now, that's what we call traditional composites, right? The one that you see on the top right. So this is an example of an isolated footing. So we have the footing reinforcement, the mat reinforcement below, and we have a pedestal, column pedestal, and column rebars are raising above. Right. So this is the foundation of this particular structure, whose picture is down below. This is a part of the superstructure. So basically, its foundations are isolated footings, which just a second, sorry. Yeah. So this foundation is made up of traditional concrete and traditional steel concrete composites. And there's a modified form of the composite in the superstructure. So basically, instead of only having reinforcement bars, we have the entire I section, and it is connected by beams, which is also structural steel, unlike concrete beams. So these are steel beams that are being connected to the I section, which is inside the concrete column. And this concrete column will be surrounded by concrete. Right after we do the form work and we pour concrete so that everything is inside. That protects the steel from fire and also gives you an aesthetic finishing, right? It's a solid finishing on the above. So that is traditional steel concrete composites, and there are advanced composites. Okay, advanced composites like that we saw, carbon fiber reinforced polymers. Again, there's carbon fiber and there is resin phase. Resin is the polymer we have, and it is reinforced with carbon fiber. So that's an example of advanced composites. Instead of carbon fiber, we could have glass fibers, and for space purposes, like spacecrafts and some of the automobiles, they might use carbon fibers, or another form of fiber called Aramid fibers. Okay, so these are some fibers. So basically, advanced composites are ones where you have fibers which are not only steel, there could be something else and you have your matrix phase, which is a resin phase, right? In traditional composite, you have concrete as the matrix, and in advanced composites, you have a polymer resin, which is the matrix. Basically, its ideology is same. In concrete, the concrete is not good at tension, so we reinforce with reinforcement bars. In composites, the polymer resin is not good in tension, right? So we reinforce it with some fibers. So these are the examples of advanced composites applications. One thing is The first one is strengthening using CFRP. The column strengthening or a girder strengthening or slab strengthening. An existing structure you need to retrofit. If you're using the same material like concrete or steel, it would be bulky, like occupying a lot of weight, and that increases the load on the foundation also, right? Because whatever you add to the structure needs to be carried down. The weight needs to be carried down to the bottom. So your entire structural path is loaded more, and it could occupy more headspace also. So for strengthening using CFRP, it's one of the most sought out procedures, which is happening right now. And you could have FRP rebars. That's one of the applications, right? So FRP rebars are good at some things, not so good at some things when compared to traditional reinforcement bars. So the FRP rebars they are very good against corrosion. It doesn't get corroded easily. Okay, and that's why they use FRP rebars in bridge applications. So FRP rebars are kind of used where bridge girders or bridge decks are being built, because your bridge is mostly over a water crossing, right? And it has its environment effect, which could be susceptible for corrosion. So in order to save it, we kind of prefer FRP rebars. And there are some other design parameters we need to look at before we finalize. So that's one of the applications. The third one is a building component, like parts of it, the column, braces, beams, railings, and deck, everything is made up of FRP. Now, this is an extreme kind of application. But this example, they had tried out, how to fabricate everything out of FRP. Now, what you see, it's not steel, it's made up of FRP. So what applications this could have is, if you want to make some observation laboratories, like space laboratories or some laboratories where they don't want electromagnetic intervention. When you make something with concrete and reinforced with steel, now steel has some sort of electromagnetism, like it's a ferrous material, so it's going to affect in that way. So they are kind of trying to use this FRP buildings, right? The entire envelope made with FRP, because it doesn't interfere with your electromagnetic waves. So that's one of the advantages, and it's a limited application, that part. The most widely used part is the strengthening part. Second is FRP reinforcement bars in bridges, not in buildings. As of now, that's the current trend. And FRP buildings, which are made up of FRP sections, it's on the extreme end, so it's not in the normal applications. Now, okay, what are the advantages of composites? Now, this is a typical cross-section drawing of a composite. Compare it with your traditional concrete, like you have your concrete and you have a reinforcement bars inside, right? Now, we have an I section, and we also have some, like these are stirrups or like tie bars. These are not box sections. Okay, so these tie bars are to tie the vertical reinforcement bars. Okay. Some of the advantages of composites. You can have economic section sizes, because the contribution by this structural steel inside, okay, this is an advantage which is not available in your traditional reinforced concrete. Now, the capacity of this particular I section, right, it's much more than your reinforcement bars, and it's easy to assemble also. You put something inside and you kind of enclose it, right, with concrete. Now, your member sizes could be designed in an economic way, but there's a catch, like you cannot take this and put it in a small building, right? See, your I section is of some minimal size, right? And for example, it could be, ISMB 200, 250 or 300, right? And you need to have certain spacing distance between your I section and your reinforcement bar. And again, from your reinforcement bar to the outer concrete, you need some spacing. So there's some minimum dimension inherently occupied by a composite cross section. Now, when we talk about economy in design, we are talking about buildings which are like kind of bigger or taller, where more load comes on it. When those kind of buildings are designed, this could be economic instead of going for a like a traditional concrete, reinforced concrete, which is bigger in size. So obviously it has more structural capacity. And another important aspect is the speed of construction. It's faster, like, because you assemble the I section, okay, over your foundation. When the foundation is ready, you have a base plate and you fix your column. Now, this could rise very tall, and you can go for 3 stories of this particular column and connect it with the beams, steel beams, like at the edge section, and then you can keep casting your column later. By that time, the other works, like you put your deck on the other floor and you pour concrete on the deck because it's already connected to your column to this I section inside, right? So your construction speed is faster because you can assemble it faster and start working on the other aspects of the construction faster. Second thing is, a part of it is prefabricated, right? Your I section is somewhere fabricated elsewhere, right? Like it's from a factory and you bring it and you just assemble it. That sheer time saving is also a big advantage here, right? And yeah, if you have less member sizes, obviously there is less load coming from the superstructure, and it is having a fire resistance compared to traditional steel. Yes, you want to build something with steel. With steel, what happens is it is susceptible to fire when fire hits on it, and it hits at a temperature enough to cause some damage, and it's going to collapse. We'll look at a case later. What happened to one of an important building, like how it collapsed. But thing is, steel structures need protection from fire. Now, in this composite sections that we are looking at right now, it is surrounded by concrete, and that kind of serves the purpose. Okay, so that is taken care of. And structurally speaking, it has some added ductility and toughness. Okay, the ability to dissipate energy, that's called that's a way of defining toughness for your lateral forces, wind or seismic. Something better than your traditional traditional concrete structures. Like in traditional concrete, you have basically what? You don't have this I section or structural steel inside, right? Now, steel is ductile and your concrete is not so ductile. You add more steel to it, and there is this concrete and you have steel structure and you have something in between, right? Composite structure which has some added structural steel inside. Now, this composite is definitely going to be much more ductile than your traditional concrete, but not as much as ductile as your pure steel structure if you want to build something with steel. So it has this added advantage of ductility compared to your traditional RCC. And it has higher rigidity and stiffness, part of your lateral system resistance. And it has higher damping characteristics because there is more steel inside. Okay. Now, one more thing is building industry is one of the largest producers of carbon emissions that we all know, and it accounts for about 10 to 12% of the total carbon emissions. If we want to build something with composites of this nature, we are doing a good thing. Like, you're not building bigger sections, right? Basically, you're reducing the size of the sections, and that reduces the size of all the components through the load paths, right? Ranging, to your foundation also. So basically, you're using less cement that goes into this construction, and you're contributing in reduction of environmental carbon emissions. This particular picture that we had discussed, in one of the previous lectures, we know when the building goes tall for a given region, for the given earthquake and wind forces it experiences, you might have to increase your column size, right? Because for lateral forces, you need to start increasing your lateral capacity itself using shear walls or bracings and things like that. Now you are more aware of, by looking at case studies of different buildings. Right. So when you go for such increased structural components inside, again going for a bulkier, or again going for something like a pure concrete, pure like reinforced concrete, traditional concrete, you might have here also for diagonals, like for the bracings, you can go for something like this, a composite diagonal also. Okay. Right. So a composite, structural composites, let's call it structural composite because your traditional reinforced concrete structures are also composites. So for distinction and clarity, okay, we will call it structural composites. The ones that we saw, which have structural steel inside, in addition to your reinforcement bars. So we can have concrete slabs. That could be concrete, structural composite beams and girders, composite slabs, composite girders, composite columns. Either you can have a steel section inside, which is encased by concrete, or you can do the other way, like you can encase the concrete by using a steel tubular section on the outside, right? You can have a steel tubular section and you can fill it with concrete inside. You can have composite shear walls, right? Shear walls, instead of walls just having reinforcement bars, you can have steel plates inside, and that's what we call composite shear walls. Composite diagonals and composite subsystems and systems, like your outrigger is kind of a system, your belt truss is a kind of system where you can have your structural steel encased or filled with concrete. Okay, now your composite slab. We look at a typical cross section of a composite slab. What happens is you have a steel beam inside, okay? I mean below the concrete deck. Now this concrete slab, we don't call it concrete slab because we call it concrete deck, because composite decks are different than traditional reinforced concrete slabs. In your composite deck, you have this steel profile, which this is the deck profile. Okay. Now that occupies some sort of space. It could be your steel deck could be like 60, 70, 80 mm height, right? And you can have concrete on top of it with some minimal reinforcement on top. You see, wherever concrete comes, you need to have some minimal reinforcement to take care of the shrinkage and temperature stresses, right? Now we'll go step by step. What's here in this picture? Like we'll come from top to bottom. You have the concrete slab, right? And that has some reinforcement. Now, the deck below is called, the reference is TR60. 60 means it's 60 mm in height. The hat section, the overall sectional height is 60 mm. So that's a deck profile. Right. So, and you need to fix this deck to the steel beam below using something called shear studs. It just cannot just sit on the beam. It needs to be anchored. Like there needs to be a composite connection. So that's what you see here. A shear stud. Okay. Here it's of 19 mm in diameter and 95 mm tall. And that shear stud is welded, okay, across your steel deck onto the steel beam. And it comes usually at some spacings, whichever can be accommodated inside this deck, or a maximum spacing of 300 mm. So all throughout the length of the beam, where the deck is mounted on top of the beam, it just doesn't sit. We need to make sure there's a composite connection, and that we achieve by using shear studs. And in order not for the concrete to flow out, and at the end we need to have some flashing, or we have a sheet for that purpose to prevent concrete from flowing at the edge of the deck. And here you can see there should be a minimum of 50 mm bearing. Like the deck needs to sit at least 50 mm on top of on top of the flange of the beam, and then you given definite edge distance and you fix the shear studs. Okay, now this is the typical cross section of the composite slab, and here's a picture of construction in reality. Okay, you can see now these are the shear studs. Right, instead of one studs we have two studs, so that means below there is a beam. Okay, now you can make sense of it because by looking at the beam above, this is a typical floor which is replicated onto the other floors. So you can see beam, a steel beam, and they have some web penetrations for the conduits to run through for mechanical and electrical purposes. Your steel deck is sitting here and it has a minimum bearing, and that it's welded using shear studs. Right, after we do that, we lay the reinforcement mesh and it's ready for concreting on top. So this is the concrete in the pipe through which the concrete flows and then comes out, and that's how it is. The composite slab is built. Right?
I had a
Yeah.
What's the 50 mm bearing? I didn't get it though.
Okay.
Just like before. Yes.
So basically, when the steel deck is mounted on the steel beam, and we have a definite length of the steel deck, right? Steel deck cannot come for indefinite length. It comes, I think, in terms of maximum 11 or 12 meters or whatever your transport vehicle can carry, and there's a standard size for that. Now we need to cut the steel deck if it's excess, or like we need to place it on the beam, right? Once we place it, how much distance we need, like the minimum distance that needs to be occupied by the deck on the flange. That's what we call bearing.
Okay. Yeah.
So once it is very short, say for example, it's 10 mm or 15 mm, and what do you do? What happens is that you take the shear stud and try to weld on, through the deck and try to anchor it to the beam below. Now the welding kind of spoils that local area, right? Now if it's at the edge, suppose this particular stud is somewhere here to the edge of the flange. Now when this particular structure is subjected to bending, it doesn't have enough edge distance. It's gonna easily get knocked off. Okay, that is one of the reasons we need to have minimum bearing. Now you guys remember the importance of edge distance in your connection design, right? You would have designed steel connections. You would have done tests, checks for the shear strength of the bolt, the bearing strength of the bolt and the plate, the tear strength of the plate, and one more thing, depending on your edge distance, or in another way, you could be giving a minimum edge distance. What is the minimum edge distance? 1.5 times your bolt diameter. You remember something like that. 1.5 times to 2.5 times your bolt diameter. Say 25 mm, 50 mm, it could be. That's the minimum edge distance that we need to give. So bearing is kind of telling you that only, how much edge distance you need to have.
Yeah.
Okay. Okay, so this is an example of a composite column. We have two cases here. The left side is the case that we saw. You have a structural steel, an I section basically inside, okay, and you have some reinforcement bars. Now, what's the need for reinforcement bars is your concrete, for example, you try to take away these reinforcement bars. Just imagine these dots. The solid dots are not there. Then what happens essentially is you are left with concrete. Okay, kind of it is far away, like the portion of the concrete which is unreinforced is kind of so high. Okay, and a concrete which is not reinforced is kind of susceptible to like shrinkage and temperature stresses. So we kind of need to add some minimal vertical reinforcement bars also, even though if it's a composite column of this nature. Okay. So what do you see? These are like the shear studs again. Now some designers would like to give shear studs Because the reason, the concept behind this is the force transfer between your concrete and steel needs to happen through what? One thing is surface friction, right? Your concrete is there, which is surrounding your I section. Now you load the concrete, right? If your steel is kind of smooth, okay, it's kind of smooth on its surface. Now there is very less frictional resistance between your surrounding concrete and your steel, right? You need, how does the force transfer from here to there so that it acts in unison? It acts like a composite. We need the composite action, right? So some designers, there are two schools of thoughts. The American code tells, yeah, the surface friction between your steel, the I section and the surrounding concrete is enough. You don't have to provide any shear studs for the shear transfer. For the transfer of the load, like through it happens through the shear concept, shear load concept. So what they do in most of the Indian design philosophy, like our codes say, no, you need to add some minimal shear studs also, all through the height of the column. Through the height of the column, you need to add some shear studs for the force transfer to happen. Okay, so that's why it's indicated. Like if your designer would like to add that, then they would add that. So this is an indication, right? So these are the shear studs, and there are some ways in which you can place your shear studs, and the spacing will be in the vertical direction. It could be 300 mm or 200 mm, whatever is there as per the design. Now you have some reinforcement bars inside as well. Now that also needs to be tied up. Basically, every reinforcement bar needs to be tied around using a tie bar. Okay, something needs to run it and like run along with it and cover it. Okay, that's why we have these tie bars. Now there's another way of composite column, which you told you can have a sectional, like a kind of the steel section on the outside, and you can pour concrete on inside. Okay. Now one of the things with this is when it is kind of loaded heavily. For example, you get this picture on the left where you have a loading diagram indicated and what is the probable profile of the steel, okay, in which it can buckle. If only your steel portion is kind of buckling, it could buckle in this way because there's nothing inside to restrain it. Like, and you pour concrete inside and you can see some shear studs. These lines are indicating steel studs, headed studs. And what happens when you have concrete portion inside, like it cannot buckle inside, right? So it has to buckle in this way. Now this is one of the design aspects that one has to consider. Your load when it goes kind of very high, like it has this susceptibility of buckling the steel portion outside. Now you need to, how do you, escape from it? You need to design your sizes, and you might have to increase your wall thickness, the steel wall thickness, so that it doesn't buckle for the kind of load your building is putting in, right? You estimate the load, how much is going to come up, and you check if your the steel wall is going to buckle or not, and that's how you check it. You make it thicker, okay, or else you see, okay, better than this design, we go for this design because it is being restrained, right? It's not going to buckle inside the structural steel. Okay, so in most of the cases, the one on the left side is predominantly used. Okay, for it's faster with the construction aspects. Like you can see a beam can come and join. There's some plate inside which is welded to the steel section inside, and you have bolt connection where this particular beam can come and get itself joined to the column, and you can cast the concrete surrounding it. So it's easier to, like in terms of construction, things could be faster here, and the connections are kind of simple. Here you might have to, weld this thin wall on the outside and form a plate to which it gets connected. So, so your connection is kind of outside the concrete, right? Then you need to protect that particular connection with something. You need to have a fireproof paint. You might have, like some connection issues, some maintenance issues also could come. So the preferred form of composite columns is that it's something that you see on the left. Now, your shear walls could be of composite sections, like you could have some plates. Again, in order for the shear transfer to have, you have some shear studs. Okay, shear wall could have something called as a boundary element. Basically, its ends are kind of enlarged or kind of, you know, like bigger in size when compared to the rest of the shear wall thickness. So in that, inside that boundary element, you can have an I section, and you can form a composite shear wall, like the one that you see over here on the top. You have a steel plate inside, and for the force transfer, they are using shear studs. You have concrete on the outside and some vertical reinforcement bars. At the end of this shear wall, at one of the portion, we call this as the boundary element, which is on the boundaries. It could be, it is definitely on either sides, right? On this boundary and something on the other side, where the boundary element usually would require more reinforcement, more steel. So basically, we are putting instead of, you know, congested steel steel reinforcement bars, we can have an I section, okay, which has increased area of resistance, right? Basically, you have more steel there. That's the purpose of it. Okay. Now, there are some design considerations which are important in doing a composite thick slab system. The one that you see, you know, like this particular span is about 11 meters, okay, column to column, and you have the main beams running. See, we got our guys with some sort of safety, I suppose. They have their safety belts and harnesses and stuff. So, and they are the ones who are like kind of helping the beams that is being dropped slowly by these cranes. You know, the cranes, tower cranes pick up the beam and kind of place it. And these are the guys who kind of guide the entire, you know, the piece of the structural component to sit, and they quickly provide some bolts inside. So it's kind of fixed. Okay. And you need to tighten the bolt later to make it permanently fixed. Okay, so what are the design considerations we have? One thing is how much strength it can take, it needs. Okay, and during the service also. Service, what I mean by service is during the normal weight or, you know, normal loading of the structure, when people are like going in and working, you have some normal live load that is there in the structure, right? So during then, you should be having not so much deflection, right? And not so much vibration also. The thing with when you go for a very thinner section, your entire floor slab right now is kind of thin, right? It's 150 mm in this particular case for this entire 10-meter span. Now, when you have a thin floor slab, what immediately comes to our mind is it's flexible, right? It's going to bend more, and it might have vibrational issues. Okay, so vibration is something that could, you know, have some consequences of effects. One thing is it doesn't feel good. Second thing is if something is vibrating, that means there is kind of force that is, you know, being applied and restored. So somewhere some sort of fatigue or, you know, some other things is going to happen. We need to check those also. So vibrational issues are typically the case, you know, your member sizes, your beams, primary and secondary beams, the size in a composite structure like this is defined by most cases vibration. In order to stop, in order to not to have vibration, you need to kind of increase the structural depth of these girders. Okay, so the structural depths are finalized not for strength design. Like you find something, you could say, for example, in this main particular beam, you determine the loads and you try to design your deck, and you have your beam sizes. It could be like 400 mm in depth, total depth. Now that's your strength based design. Like for the loads that is coming in, you do a bunch of calculations and you say you need only 400 mm depth beams. Okay, Now in this case, when you do a vibration analysis check, okay, there are some formulas and there are some softwares which does the vibration analysis based on what, like they do based on what is the walking frequency of the people working there. Like if it's an office building, what's the frequency which can hit because of walking, because of the live loads, and that should not match with your inherent frequency. You remember that the resonance concept that we saw, your excitation frequency, basically your building occupancy frequency, people walking, running, and things like the machinery running, that frequency should not match your structure's frequency, right? So when you do that, you might end up with making the structure more rigid, like basically your beam depths could be now larger in order to avoid that resonance. And that's why I say your vibration analysis would determine your member sizes. You would end up with providing members which are like now 600 mm depth or 550 mm in depth, where your actual strength and serviceability, like your deflection requirements could be fulfilled by only a 400 mm deep beams. But your vibration would tell you need to step up, you need to make your system more rigid, you need to put bulkier sections. Okay, so that's what happens. So vibrational analysis is very important when you are going for thin sections. Okay. Now you need to have your architectural considerations and functionalities like MEPs, right? Mechanical, electrical, plumbing conduits will be running through your buildings, and you need to make kind of penetration, web penetrations for that. I need to check your beams and girders for that, and it would occupy headroom. So you need to figure out you're going to provide a false ceiling, and that's gonna reduce your headroom. So your entire floor height, you need to determine, okay, instead of 3.2 meters, let's put it 3.5 meters, because your net floor height is something that you can work with. So shear studs are important. Shear studs are the ones which provide the composite action between your deck and your beam below. If you place something, just place it without your shear studs, which is connecting the deck to the beam below. The kind of deflection it has when compared to a proper connection using shear studs is very different. Okay, so a composite action is that we call. Okay, so that is a design consideration. So shear transfer that we saw in a column which is having shear studs, which is very similar to a shear studs on these beams in order to transfer the force through shear. Okay. Then creep and shrinkage effects. Yeah, heavily loaded columns. The concrete tends to over a period of time compress a little bit more than its initial stages. That's what we call creep. So that consideration we need to do. And for this large structure, it could deflect more. So what happens is we have a camber. What do you mean by camber? This particular beam, you can see it is kind of slightly bent on the upward side. It might not be very clear from the picture, but when you measure it, this secondary beams are like kind of bent on the upward side by 15 mm, and this primary beams are kind of bent on the upward side. When you measure the top of your middle portion of the beam and the top of the end portion, there's a difference of 20 or 25 mm. So that's what you call cambering. You provide the bend in the opposite direction so that when the building gets loaded, it's gonna negate that camber and needs to put in more effort to make it deflect downwards, right? So if you put something flat, it's going to deflect down. If you're going to make something inherently cambered on the top, then you need, for the service loads, it's going to come down. For the extreme loads, it's going to come down a little bit, but it's not going to deflect as much as the case without a camber, right? So that's the purpose of a camber. Now, obviously, when there is steel when there is steel put in, we need to consider the fireproofing requirements. So in this case, the column is fireproofed by the concrete surrounding it. What happens to the steel beams? These are also kind of coated with fireproof material. Okay, something like vermiculite or fireproof paints. So that needs to be coated, and we need to protect it from fire. Then what's the erection sequence and construction sequence? how fast we need to erect and what are the logistics we need, those kind of planning. Okay, these are the things that we need to take care in the design also. Okay, this is a small case study here. The column to column distances are about 10.8 meters. We are talking about the same building that we saw in the pictures before. And you can see these are all composite columns. We have an I section inside and surrounding concrete. And there are steel beams. And you can see there are some notations which are mentioned. Okay, what does that mean? Okay. Now you have a beam. This is a primary beam, right? Because it is connected to the column. And on the one side, you have a secondary beam being placed here at two different points. Now, this on the top, you have a number. That's the indication of the member size. So in the legend, you will have what does that number 4 means. It's usually the section size. OK, what depth, what is the flange width, what is the thickness at all. Now below you have a notation called SC, which means shear connectors. So shear connectors, which are 25 mm, like mm in dia, M25, and that placed in 2 rows at 32 places. So basically we need 32 into 2 numbers of shear studs placed equidistantly along the length of the beam. Okay, and C stands for camber. So camber is 30 mm. So that particular beam is prefabricated with a camber and upward deflection of 30 mm. Okay, that's what this indication means. And S1 means it's slab 1. Okay, and when you go to the legend of S1, it will tell you how much reinforcement, what the rebar diameter and what is the spacing that needs to go and what is the grade of the slab. It's M30 or whatever the grade. So that's M1. Okay. So this is an example of what would you read from a composite section, okay, a deck section. Yeah, I think here the camber is 30 mm. In some places, see here, it's 45 mm. You can see, okay, it's basically there are, like 4 secondary beams which are being, connecting here, and then the loading could be kind of high also. So you have camber which is more 45 mm here compared to other places where it has 30 mm. And typical spacing between a primary beam and a secondary beam and in between the secondary beams is around 3.6 meters. Okay. This portion is like 1/4 of the building. You have some central shear walls here. Okay, and you have some stairs and some shear walls on this side. So basically, there you can imagine by replicating this side of the building on the other side, it's the same thing. Okay? So this is a representative sample. As I told you, when you go to the composite steel deck schedule in the legends, you have what do you mean by S1. S1 is the slab mark. Now they're saying the total slab thickness is this, and your steel deck, so which is TR60 profile. Now this is a proprietary product from JSW Steel, the company that delivers the steel deck. So their cross-sectional height, overall height is 60 mm, and the steel deck is only 1 mm in thickness. Okay, your grade of steel is M30, and your slab bottom reinforcement is 10 diameter rebars at this much spacing. Why this weird number 333 is your center to center distance between your steel deck profile is 333 meters. Like I need to show you a clear steel deck profile because I did not have it here. Just a second. SW steel deck. Where is the product? Yeah, so we were talking about this TR60, right? And yeah, this is the picture that I took, and this is the cross-section profile. Now, This TR60 has this overall depth of 60 mm. And you can see the profile is not smooth. It has some corrugations and embossements, which is very important because it needs to, one thing is it needs to stick to the concrete, right, which is being poured on top. Now, your concrete will be poured and it will occupy these cavities here, the valleys and troughs, and 60 plus 70, your total concrete deck thickness would be like 150 mm, right? Now, in your steel deck, you have this profile. The reason I told you is one thing is to stick to the surrounding concrete. Second thing is, if you have a profile without this, it's kind of smooth and it doesn't have these corrugations. For the kind of span it has, it will deflect more in order to make it like, it's something like folded plate example we saw. You remember, like we took a paper, if it's flat, it's going to bend more, and you have some sort of folds inside them, it's going to be more stiffer, right? So that's what they're trying to do here. When you place the deck, where's the case? Yeah. The deck will be cut, and sometimes it could be placed. Sorry. Yeah. It needs to, be placed within the span, right? 3.6 meter. Like, so if your profile is not corrugated like this, it might bend more within this particular span itself. So in order to avoid that, and for much more longer spans, this company, they have some sort of profile like this, so that you don't need anything below, like you don't need a prop to be placed below, so that it doesn't bend excessively. So here they are telling TR60 profile enables unpropped spans in excess of 3.5 meters, right? So I think around 3.5 or something more than that, it need not be propped from below. It need not be supported from below. And it comes in these different thicknesses, which are around 1 mm, and it's of steel grade 350. Your minimum yield strength of this plate is 350 MPa. Okay. Yeah, so slab top reinforcement, slab. Okay, the reason I went to that section is when you look at the section profile, your bottom reinforcement can sit in the valley portions only, right? That's in the bottom of your steel deck. Now your center to center distance between your valleys is kind of this number, 333. And your top reinforcements are again 10 mm diameter bars at 200 mm spacing. And the other direction, distribution direction, like you need to put rebars in both the directions. It's again the same. Here for this particular slab S2 and S3, the loading could be really high. So the structural engineer is telling you might need a prop below it. Okay, for these slabs. And if it's a cantilever slab, you might have to provide extra additional reinforcements. So that is also indicated. Now, this is a typical example of how the slab deck, like it's kind of ends where you have a facade that is being connected to the slab deck slab, and how the reinforcement is kind of forming a U bar and ending here, right? As I told you, number 3, number 4 means it's the plate girder number 3, number 4, and which has this particular profile. So it's 150 mm in width, flange width, and its depth is 500 mm. 11 stands for thickness of the flange, and 8 stands for thickness of the web, and its grade is 450. Minimum yield strength of this particular plate girder, okay, it is 450 MPa. Last slide of this particular composite, presentation is we have a comparison of design. Okay, now I'm not going to ask you to do some calculations, but just look at what happens when you have a typical reinforced concrete column and you have a composite column. Okay, now how much load it can take and what is the member size it can economically gain. So on the left side, I took an example where the column load is 5000 kilonewton. It's made of M40 grade and Fe 500 steel. Okay, reinforced, the reinforcement bar steel. Now the column size I designed using 400 mm by 700 mm, and this is the overall area. AG is the gross area, so 700 multiplied by 400. That's basically about it. And I'm providing 8 numbers of 20 diameter rebars. Okay, and that's 0.9% reinforcement. The cross-sectional area, like 0.9% of the cross-sectional area, is the reinforcement that I'm providing. So 8 numbers of T20. The total area of the reinforcement bars is this 8 into multiplied by the individual reinforcement bar area. And the column capacity, we have this formula 0.4 FCK plus 0.67 FY. FCK is the strength of the concrete, which is 40. AG is the overall concrete area, the gross area minus the reinforcement, because I'm accounting this for only the concrete, plus 0.67 FY. FY is the steel into area of the steel. Okay, this is the formula that you find it in IS 456, and it's a basic formula for column. You can use this, you can remember it if you want to, but the idea is you are getting a capacity, column capacity, when you plug in this formula and all our numbers here, and you have a capacity. Now, my capacity is more than my assumed design load, so I'm good. So by how much factor? Like kind of like 0.95, like it has 5% reserve capacity, right? So we have designed something which can take up to 5,282 kilonewton, not only 5,000 kilonewton. That's what we need to design. Like your design should be like something around this range. It should be optimum. You cannot design for something like 10,000 kilonewton because that's only 50% economical, right? So okay. So this is a case of an RC column. What if we use a composite column? Okay. So what I'm doing here is I'm going to compare two different things. I'm going to make the composite column size to be same as my previous case. Okay, 400 by 700 mm. Now your gross area is the same. Now I need to provide minimal reinforcement. I told you, I'm providing 0.43% of the longitudinal rebars, the vertical rebars. So 6 numbers of 16 mm dia rebars. So that's the area of the rebars. Now structural steel, I'm going to plug in a steel, an I section, which is 300 mm in depth, 200 mm is the flange width, and 12 mm is the thickness of the flange, and 10 mm is the thickness of the web. So that occupies effectively about 2.7% of the cross-sectional area, and this is my area of that particular structural steel. Your formula is kind of the same, like 0.4 FCK into portion of the concrete plus 0.67 FY into portion of the steel plus 0.87 FY into portion of the structural steel. Now I need to plug in those particular values, which are relevant, and I'm getting a capacity of 7,000. So basically, with the same column size, and I'm reducing the number of vertical rebars, I'm putting in a structural steel member inside. Okay, I'm getting an increased capacity, right? Obviously, because you're using a structural steel inside, you're making it kind of a composite column, right? So my design capacity ratio is now 0.71, right? Now that's a visible advantage right away, right? You can have a case where the design load is much more, still this column would perform. Now, second thing is I want to reduce the column size, okay, for the same design load. Now I'm taking my composite column to be 400 by 400. And I'm providing lesser rebars, like I'm kind of providing 2 numbers of T12, okay, like which is in this case is 0.4. Because I've reduced the column size also. It's now 400 by 400 instead of 400 by 700. Now I'm providing a much more less structural steel compared to the previous case. I'm providing a 200 mm depth instead of 300 mm and a 16 mm depth, thickness flange and 10 mm thickness web. Now that's kind of increased if you look at the proportional cross-section area, but that's kind of, but it's actually less than your previous case. Okay. And your composite column capacity comes out to be 5,000 kilonewton. Okay, and our demand is 5,000. So either you can do this, you can have column size, same column size, and it can take much more load, but your actual design is only for design load of 5,000 kilonewton. You can have a reduced column size, and this is the advantage we have in design and using a composite column. Instead of an RC column, a composite column is much more smaller in size, and you can make it take more load also. Okay. I'll share you this particular PPT. You can have it for reference. Any questions on this before we jump on to next topic? We have like 15 minutes more. I'll cover a few parts of structural collapse, things that you like to talk about. And you have any questions now, guys? Any questions? I'm just making others attendees. Guys, no questions. OK, we'll go to the next topic then. OK, so the next lecture series would be about structural collapses or failures. OK, and as I told, we're going to learn from structural failures what happened and how to design it in a better way. Okay. Now, this particular example is from the UK, which happened in 1968 near London, in the outskirts of London. So this building is called Ronan Point. And basically in 1960s and 1950s, a lot of prefabricated, housing came up, all across Europe, basically, because they had this immense demand of building, more buildings quickly, because they had a huge loss in the wars before, right? The World War I and World War II. A lot of buildings were destructed, and now in order to bring back the economy and also provide housing for a lot of people who lost their houses, homes in the previous case, they wanted something more quickly to be built. So prefab had its kind of mass housing, origination of prefab in kind of mass housing. Prefab was before, but here people started using it really in like many instances. Now, during this initial mass housing using prefabricated components, had a lot of things which they did not engineeringly, think through before they can implement it. So it had some flaws. So you can see after this particular period, 1960s, they kind of did not venture into prefabricated things for some reasons until now. Until now, Europe is again coming back with designs using prefabricated components because engineering has improved a lot and analysis and testing has improved a lot. But during its initial stages, this was the pretext of why prefabricated structures were built in mass scale, because for the sheer need of providing housing for many people after the wake up of World War II. Okay, so what happened in this case is it was built, and after 2 months, one fine morning in around 5:30 or 5:45 a.m., a person in, I think, from the top, like 3rd or 4th floor from the top, she went to the kitchen and switched on the gas, supply, and I think she triggered some switch or something because the gas was already leaking from previous night. And yeah, so immediately it was an explosion. Okay, it was an unfortunate explosion, and because of the explosion, what happened was one of the walls, now it's a load-bearing wall. This building doesn't have columns and stuff. All these walls are, and all these components are prefabricated and assembled, and these walls are load-bearing. Okay, the wall kind of like flanked away, it like fell off. It was like pushed away. Okay, now it pushed away, and what happened was there obviously you don't have the wall which was taking the load, and the weight of that portion of the building from 4 stories top was too much, and it had kind of a domino effect, and it, so that particular wall failed, and there's nothing to take care of the load from the top 3 floors, and everything started collapsing in a domino effect. A progressive collapse. That's what we call as a progressive collapse. It's not local, it's progressing. Like because of one particular failure, one structural element failure, it is leading to the failure of its surrounding structures. Like it's going to pull down the entire building. So this portion of the building, everything came down. Luckily, only this portion of the building. But of course, a few people died and many people were injured, and this happened. So what went, the mistake was, in the initial prefab constructions, the connections were kind of very weak. The connection between the slab, okay, and the wall they had kind of very weak. During investigation later, they found out it was designed by an inexperienced engineer, and instead of concrete inside, they had some newspapers inside. In the connection area, where instead of it needs to be filled with concrete, they had newspapers and stuff like that. So it had some construction issues, and it also had design issues. The connections were not properly designed, detailed, and constructed. So the slab and the wall, instead of having a good connection, when the explosion happened because of the incoming force, that slab and the wall connection was not good, and the wall kind of flew away. And that is one thing, the connection failure. Second thing was, it was a progressive collapse. So one thing like this happened, the weight of the entire structure, they don't have other ways to go. That wall was the only load bearing, or what do you call, the load path, what the weight of the other things on the top was like relying upon. So you don't have redundancy in the structure, you don't have other load path in the structure. So it leads to failure of that critical structure, and everything progressively collapses. Okay, now tell me how a connection should be, or what do you mean by having a good connection? Anyone can say, what is the primary requirement of a connection in anywhere? Like you have a chain, and you're going to connect a chain in order to make it a longer chain, right? So what needs to be the function of the connection? What things the connection should satisfy? Anybody got anything to say? When you are designing a connection, it could be any sort of connection, and you're going to construct it. It needs to serve one important purpose. Guys, what do you think? What should a connection do? Of course, it should not fail, right? So basically, when you're designing the connection, the connection should be stronger than your material. If you're going to connect a chain to make it a longer chain, your connection component should be really strong, because when it is tested to failure, your failure should not happen at the connection point, but it should have at the material point, somewhere in the member. Like your connection should never fail. Your connection should be stronger than your member or your element. Okay, that's one thing that you need to always design for. So what are the lessons learned from this? You need to have to analyze everything, like things could go wrong, because if you are constructing something on a mass scale and it's kind of quick housing, and you need to check everything, right? Second thing is prefab structural connection weaknesses was also identified. In this case, the engineering has not developed, like the concepts has not been developed so much how to have kind of very strong connection in prefabricated elements. Second thing is, if something is failing, there should be some other members to take care of the load transfer path. Okay, a structure cannot rely on only one particular element, because something is knocked off, it should not be progressive in failure. You should have redundancy in the structure. It should not be only one particular load path. It should have, the important parts of the building should have multiple load paths. Okay. Okay, so second example we'll see is this particular hotel. Now, don't think like this entire building came down, not like that. So there was something that happened in here. Here they had a ballroom, basically a kind of party hall, and they had some walkways, like something you see here. Like there's a walkway which is connecting the third floor, right? So 1, 2, 3, right? On the third floor, there's a walkway, and similarly, they had two walkways over here on the second floor and on the 4th floor. Now that walkway collapsed during a actual function. There were hundreds of people on each of the walkway. It was very unfortunate that about more than 100 people actually died in this particular collapse. Right, it was one of the biggest in the United States until the 9/11 collapse happened. So we'll see what happened in this particular case and what led to the collapse. Okay, this is a very interesting case because it teaches one particular thing, which is, we'll see in a moment. Okay, guys. Now tell me, any one of you, like if you are okay, this is the original design. Okay, on the something that you see on the left side. So as I told you, there are two walkways which were here, which was on the 4th floor and on the 2nd floor. Now the original design was something like this. You have the tie rods, which is the hanging rods, which is connected to the ceiling, and you have your top walkway, the 4th floor walkway. And how it is being connected, you have some nuts over here, like a bolt, nut, okay, that's a connection over here. And you have the second walkway below the 2nd floor, and that is also connected to your hanging rod using the same kind of connection mechanism. This was the original design and the proposal. Now the contractor, when he saw the design, he said, okay, this is kind of difficult because in order to have this kind of arrangement, I need to make threads all through the tie bar in the hanging rod length in order to fix it later. So okay, can I have this kind of alternative? Now usually what happens in the structural design which is happening in the United States and which is coming right now in India also is, a designer would design something and would provide design drawings. There's something called fabrication drawings, which is being created by the fabricator or the contractor. Now the contractor gets your design drawings. Now design drawings tells you overall like what needs to be built in what way and all. In order to make individual drawings so that you can take the drawings and go to the fabrication factory and build the components accordingly, you make something called shop drawings or fabrication drawings. Okay. Now that is the responsibility of the contractor or his sub agency which he has hired to make shop drawings. So the shop drawing, during the production of the shop drawing, the contractor gave this kind of an alternative proposal. Now again, this needs to be verified and signed by the designer. He needs to look at all the shop drawings created and he need to check, okay, if this is okay or not, and he gives an approval and stamping on each of the fabrication drawing, and then work is carried on. Okay, you get that to the fabrication yard and you start making those components. Or if it's for concrete also, you need to start pouring the concrete right on the site. Now this was a proposal given by in the shop drawings by the contractor, and the structural engineer, without verifying it, he approved it. Now you guys tell me what is the difference here? Any one of you can please tell me if this is okay or not okay. If it is not okay, then what do you think is wrong here? Basically, you have a tie rod, your hanging rod, where both of the walkways needs to be hanged. Okay, this is the first arrangement. The second arrangement is easier to construct. It's easier to erect for the fabricator and the contractor. Okay, so he has proposed this. Now, can someone tell me, is it right or wrong? If it's wrong, what is the reason it's wrong? I want one of you to speak up. Somebody, come on.
Yeah, in the first one, the load is like suspended from the up, like there would be members at the top, and so the load has been distributed equally. There is equal distribution. But in the second one, as the member is broken down into two parts, the load distribution isn't correct. That's what I think.
The load on what you're talking about, the hanger which is taking the load?
The hangers, yeah.
Okay, so you're telling in the first case the load is going to the hanger in for example at this level, and you have a floor below, which is also putting its weight on the hanger at this
Yeah,
level.
it's a continuous member. So
So in this case, your hanger rod in case number 2, the arrangement number 2. Okay, so the first rod is taking the weight of this walkway. Okay,
yeah,
right, and your second rod is also taking this kind of walkway. Now it is just, I mean, both seems to be taking the load only, right? Same load.
But still it's broken. That's why, like, the member isn't continuing towards the top, so it isn't connected to the main structural member, which might be at the top.
Okay. Okay, so that's your guess. Okay, we are somewhere there, and we'll wait for somebody else's response. Anybody has got anything else to say? Guys, what do you think is right or wrong with this case too?
Maybe the joint at the top. So in the second case, so the way the walkway, the lower walkway is hung onto the first the upper walkway. So in the first scenario, like that, the bracing or the joint happens below the walkway, but here it could be that that entire weight of the lower walkway is kind of getting it's kind of pulling down the upper one. So maybe it could be like a like a case of where it kind of gets dragged down completely because of that.
Okay. So I get your point. We are coming somewhere closer with this answer, like I mean, both of your answers. So one thing is what she's telling is, in the first case, you have your connection, the nut basically, which is bearing the weight of the walkway. Now the nut is at the bottom of the walkway, and through which it gets transferred. Now the second case, what she's guessing is you have the connection over here on the top. Okay, that's kind of pressing down, and there could be difference in that. You're somewhere closer, but yeah, like you think in that aspects. Now what happens in addition to this kind of an arrangement, in this kind of the connection setup, not only that it is on the top, there's something that is happening to this and to this. Can anyone think more in this line?
Maybe these two connections are very close to each other, so the the between area can become very weak.
Yeah, I mean that's a way to, but the structure did not fail of that reason. I get your point. There is a lot of shear transfer that is happening within this zone, but the collapse was not because of that reason. Just think, the extent everybody try to think what happens to this particular, the nut over here.
Adding to what Anushree said only, because the upper walkway is getting like pulled below because of the load of the lower walkway, there is much more there's much more load that the lower connection have to take.
Yeah, you're right. That's the reason. So what happens is, because of this kind of an arrangement, what happens is this particular tie rod or the hanger rod in the second case, now it's carrying the weight of your lower walkway, and in addition to that, it is also, I mean, that load is being transferred to this nut. Okay, load number 1. Second thing is this walkways, like fourth floor walkway is also directly transferred through this particular nut. So this connection over here is experiencing twice the force than it is actually designed for. In case A, you have the upper walkway sitting. Your tie rod is, it can take. Now the tie rod did not fail. Your hanging rod did not fail. It is, suppose it was designed to take, if you look at this section on the top, which is above the walkways, it's the same. It's experiencing the same load. Okay, in both the cases. So your tie rod did not give in. What happened was your bolt here, instead of this connection over here, instead of getting only weight of this one slab, now this guy here is experiencing the weight of both the slabs by this simple arrangement. So one thought like, okay, this is a small arrangement that we can get away with. It's easier to construct, but back check, like somebody has to back check. I told the shop drawing needs to be checked by the structural engineer again and approved, but they did not do it. It did simply, like nobody, actually looked at this in detail. They thought, okay, it's going to be the same, and they approved it. And what happened was the collapse because of that. So this is the first case. Okay. Now you have, because of the load coming in, you have the weight. For example, P is the load, right? Now that load is transferred through the nut, and your nut, this case original design made, is experiencing only P. Now you have a lower load below, right? There's another floor slab that is coming in. That is what is mentioned here, P. So your entire tie rod, the hanging rod force is this 2P. Okay. Now here is the same case, 2P is hanging rod force. But what happens to this particular nut because of the arrangement differences? This P from the floor below, 1P plus the floor weight from this same floor, and another 1P, like so you have 2 times the load on this particular nut. And the box section through which this rod is passing is also arranged like this. And that's what gave away. The load was too much, it did not bear, and then you can see the failure of this cross section. So that's the right guess, guys. So this is what happened. A small detail change could cause a catastrophe like this. Okay. So what I mean, if they had a different kind of a section instead of a box section, which can open up inwards because of the force, if they had something else, if they had welded up in addition to the box, like in addition to the bolt and nut arrangement, and I don't know if they had some sort of arrangement where this, box, how it is made up of. It is made up of a C section here and a C section here, right? It's kind of welded at this, like where it is joining. So that weld also that gave away, and because the force was twice the normal conditions. Yeah. So this was a grave mistake. Somebody did not look through, and about 114 people lost their lives. So the big lesson that we learn is the design drawings. Once the shop drawings are made out of the design drawings by the fabricator or the contractor, it needs to be verified. So guys, like if you're in a position somewhere, like, and you're seeing somebody is creating a design drawing, somebody is actually creating a shop drawing which is based on the design drawings, check if it's verified or not by the original designer. Okay. And second thing is mode of failure. Second thing one person could have also avoided is something going to fail how they want it to fail. Now this is an immediate failure, right? Something gets snapped off quickly. It's a brittle failure. Now the sequence of failure also one has to design. One has to say, okay, if it's something is failing, I don't want a quick brittle failure. I want something, like take time and fail. I want ductile failure. I want the steel to yield first. And you find the load path, what happens? And you size your members and connections in such a way, your steel starts yielding, and you have a warning or indication, because when you steel starts in, steel is not going to snap off immediately, right? If it's going to yield, it's going to take some time, and here's some sufficient warning. You can see visually, okay, it is being stressed so much, and there's a deformation happening. That's what we call a ductile failure. In a ductile failure, you can have a sense of warning, okay, something is being loaded heavily instead of something snapping quickly, immediately, right? So that sequence of failure also one has to design. Your load path and your sizes across the load path needs to be designed so that you have a ductile failure, not a brittle failure. Okay, so we'll stop up to here today, and we'll see some more cases possibly in the next week. Okay, you guys have any questions? A good job answering on this particular case. Any questions, guys? Or we can stop for today here.
Thank you.
No.
Okay. Thank you so much.
Thank you.
Thank you.
Thank you.
Hello. Hello.
Yes.
Yeah.
Yes.
Hi, Guru. I just wanted to know, when you download the attendance list, it downloads presenters and attendees, right?
Yeah.
Okay. Okay. Cool. Cool. Because
Yeah.
sometimes the presenters and attendees are different, so hopefully
Okay.
both of them get included.
I'll double check that. Hold on, please. Yeah, your name is in the attendance list. That's verified. Anybody else who are presenters during the session? Please let me know. I'll just verify if your name was there. Rishi Raj, you raised your hand. Okay, you are a presenter. I'll just see. No, Rishi, I think you joined in later. When I took the attendance, you were not there.
Okay, okay.
Rishi Raj, you were not there. So when did you join? What time?
I don't know, but I joined in late.
Okay. So okay, I'll add your name right away. But so anybody else joined in late and still there, then only I can talk to them. Okay, except Rishi Raj, I think everybody has joined in before. I remember, yeah, Rishi Raj joining in later because you were a presenter. Then I had to make you an attendee.
Hello. Sir, I
Yeah.
joined 2 minutes late after the attendance was taken.
Who is this? Just a second. Who was speaking? Ritik. Okay. Okay, I'll add your name also. Thanks.
Thank you.
Yeah, actually, same. Even I'm not sure when you took the attendance. Like, I don't know if I was there. Like, I joined on time, but I don't know.
Join the time. I took the attendance around one. Let me just see. I took it around 1:35 or something.
Okay, okay. Like, because I had lost connection in between for like 2 or 3 minutes, so I'm not sure when you took.
Wait, let me check your name. Yeah, your name is there. Right.
Okay, okay. Thank you.
Okay, guys. I think we don't have any other questions. If you have, please ask, or else you can take leave. Thank you. You guys have some other class today later. You got an some encounter session, right? And nobody is here.